Today, we're going to talk about something kind of wild, a hidden and potentially catastrophic flaw in Bitcoin's early code. And then, we'll get into the absolutely ingenious solution that not only patched it up, but really unlocked Bitcoin's future potential.
So, let me ask you this. Can a digital signature be changed, even if it's perfectly valid? It sounds impossible, right? I mean, a signature is supposed to be the final, cryptographic seal of approval. But here's the crazy part. In the early days of Bitcoin, the way a signature was created meant it could actually be tweaked after the fact without making the transaction invalid. This tiny little detail created a massive vulnerability, and understanding it is really the key to seeing just how much Bitcoin has had to evolve.
All right, so here's our game plan. First, we're going to uncover this hidden flaw in Bitcoin's design. Then, we'll see how it could be exploited in a real-world scenario with our old friends Alice and Bob. After that, we'll introduce the hero of our story, the SegWit solution. We'll break down exactly how it works, and finally, talk about what it all means for the future of Bitcoin.
Okay, so let's dive right in with this hidden flaw. It's got a fancy technical name that might sound a little intimidating, but the concept itself is actually pretty straightforward. It's called transaction malleability.
You see, every single Bitcoin transaction has its own unique ID. It's like a fingerprint, right? And you absolutely need that fingerprint to be permanent, especially if you want to build more complex systems on top of Bitcoin. But in the original protocol, the signature itself was part of the data used to create that ID. So if you could change the signature, you could change the ID. And that, my friends, is a huge problem. It made things like the Lightning Network basically impossible to build safely.
And what makes this flaw so sneaky is that it's not some hacker from the outside trying to break in. No, this is second-party malleability. That means one of the people inside the contract can mess with their own signature to get an advantage. It's an inside job.
Think of it this way. It's kind of like a handwritten signature. I mean, even if you sign your name twice, right now, those two signatures will never 100% identical. Early Bitcoin signatures had a similar weird property. A signer could use a different random number in the math behind the scenes to create a slightly different, but still totally valid, signature for the exact same transaction.
So how could someone actually use this to, trap somebody's money? Well, let's look at a classic crypto example featuring two characters you've probably heard of, Alice and Bob.
Okay, let's walk through this whole trap. So, Alice and Bob, they lock up some funds in a joint account. To keep things safe, they first create and sign a refund transaction. We'll call it TWEX1. This is their escape hatch, and it's built to spend money from a future transaction, TX0. So, with that safety net in place, they both go ahead and sign the main transaction, TX0. But here's where the trick comes in. Bob takes his signature for TX0, messes with it just a little bit, creating a new but still valid signature, and then he broadcasts his version to the network. Now, if his version gets confirmed first, the original TX0's ID, the one Alice was counting on, is now totally invalid. And a refund transaction? Yeah, it's completely worthless. This slide just lays it all out, plain and simple. On the left, you've got the transaction Alice thinks is going to happen with its specific ID. On the right, you've got Bob's sneaky version. The only difference is that tiny change in his signature. But look at that. It results in a completely different transaction ID. Both of them spend the same money, both are perfectly valid, but only one of them lets Alice's refund actually work. And this is the bottom line, folks. Bob has successfully broken the chain of trust. Alice signed a refund based on a transaction ID that now, for all intents and purposes, doesn't even exist on the blockchain. She can't get her money back, and Bob now has all the control in their joint account. This wasn't just some theoretical what-if. It was a real roadblock to building secure, multi-step contracts on Bitcoin. Okay, so obviously this was a massive problem. It needed a fix. And thankfully, the developer community came up with this incredibly smart and elegant solution, which we now know as segregated witness, or just SegWit. The whole solution really boils down to this one simple but brilliant question. If the part of the transaction that can be changed, the signature, is the problem, well, what if you just took it out of the equation? What if you calculated the transaction's permanent ID before you ever even added the signature? And that, my friends, is exactly what segregated witness does. I mean, the name says it all. It segregates, or separates, the signature data. That signature data is called the witness because it witnesses the authorization to spend the money. By moving this witness data into a totally separate part of the transaction, the core data becomes unchangeable, and so does its ID. So the idea is awesome, right? But
How on earth do you make a change that big to a massive, live, decentralized network like Bitcoin without, blowing the whole thing up? Let's get into the mechanics.
And what's really interesting is that this wasn't a new idea. Developers had been kicking around this potential solution since as early as 2011. The real hang-up, the real challenge, was how to roll it out without breaking the entire network. The big breakthrough came in late 2015 with a plan to implement SegWit as a soft fork, basically a backward-compatible upgrade.
And that choice was absolutely critical. See, a hard fork is a clean break. It's not backward compatible. Everyone has to upgrade. Otherwise, the network can literally split in two. A soft fork, on the other hand, it's way more graceful. You add new rules, but you do it in a clever way so that old, unupgraded software still sees everything as valid. This lets the network adopt the new features slowly over time.
So how'd they pull off this magic trick? Well, it's pretty slick. To an old, unupgraded node, a SegWit transaction looks like a weird but totally spendable, anyone-can-spend transaction. But the new SegWit-aware nodes know there's a secret key, that witness data, tucked away in a new spot. So the old nodes just shrug and ignore the new data, while the new nodes know to check it and enforce the rules. It's a really brilliant way to add new features without breaking what's already there.
And the result is exactly what we wanted. The signature, the witness, is now safely separated. The transaction ID is calculated from data that absolutely cannot be changed by any cosigner. It's now fixed, it's permanent, it's reliable. And just like that, second-party transaction malleability, it's a thing of the past. Problem solved.
But SegWit was way more than just a bug fix. It was a really crucial step in Bitcoin's evolution. So let's zoom out for a second and see how this fits into the bigger picture. Fixing malleability was the mission, for sure. But in the process, SegWit was actually part of a much bigger trend in Bitcoin's development, making the system more abstract, more flexible, and way more programmable. It created a clean separation between the what of a transaction and the how of its authorization.
This table here really shows you what I'm talking about. You start with the original white paper, super simple concepts. A public key says who can spend, a signature is the proof. The legacy system made that more abstract with scripts, and SegWit takes it even another step further, with witness programs defining the rules and the witness structure providing the proof. Each step makes the whole system more and more powerful.
And that is the real takeaway here. This increasing abstraction isn't just for tech nerds to argue about. This is the stuff that lets developers build really cool, advanced technologies like the Lightning Network, create more secure wallets, and design far more complex and reliable smart contracts, all on top of Bitcoin.
The story of SegWit really proves that Bitcoin isn't just some static piece of code. It's a living technology that evolves to meet new challenges. It fixed a critical flaw from its past, but in doing so, it opened up a huge door to its future. As the demands on the network keep growing, it really gets you thinking, right? What new challenges are out there that will force Bitcoin to evolve all over again? And what in the world will that evolution look like?